I used to take my book and study on my bicycle sometimes.
What?
Just take your book.
Yep.
Yes, alright, so let's get started, as they say in France. I put an accent in there, but not really big. Okay.
It's beautiful.
Started. So there's a couple of things I would like to do today. For one, there is an exercise on when we solved the Newton's second law, right? In the particular case that somebody was pushing or pulling indefinitely. You might remember this, that we were doing on Friday this exercise. Here's Newton's second law in a relativistic setting. We derived this, so it's very nice. We also discussed that this part is inherently much more difficult than it is in the Newtonian case, the non-relativistic case. Usually Newtonian physics can be difficult because the F's are difficult. The force, it happens to be a very crappy situation, right? But here in relativistic physics, the equation itself, the left-hand side is already difficult. Why? Because the thing that you're looking for, which is x, and if you will, therefore also its derivative and its second derivative, appear in this thing in a very non-trivial way. In Newtonian physics, it's just m times the acceleration, and here it is the acceleration, and yet another v somewhere hidden inside the gamma to the 3. So that makes it a very difficult differential equation, regardless of how difficult your f is. And we saw a snippet of that on Tuesday, when we saw that even the simplest f that you can put in, namely a constant f, so it's f that does not depend on x anymore. That's the simplest situation you can have, aside from f is 0, and that by itself already gets, yeah, I mean, the function that we gave was already difficult, right? You might remember what it was. I told you what the velocity that obeys this equation, and I'm reciting from memory, so please feel free to correct me, but I think it was this, ftcn squared square root. Somebody check? Because literally I'm reciting from memory now.
Yeah. My memory says the same, but
Yeah.
Yeah? Okay. And I just postulated the solution. I said, well, this solves that equation. It's going to be a headache if I did not tell you that equation. I just told you, well, here's an equation. Find v. Non-linear differential equation, difficult time. So, am I going to ask something along these lines on the exam? No, because if this were a course in differential equations, yes, then that will be a good exam. But this it has to do with physics, not to do with mathematics. I'm going to ask about physics. And the question then is not where do we get this from, but what are its properties? And the property that we looked at a couple of days ago was, well, if this is what comes out mathematically, then you can show that ultimately it cannot go past beyond c, right? I mean, it can get to c if you pull for an infinite amount of time.
Sorry.
No, it's fine. It's, might have to fight for you. Oh, there we go. Now, that this thing comes out not bigger than c, you can only approach c asymptotically. We actually already saw from this, right, from the main lecture, that this thing will always say that things cannot go faster than c. You can only approach it asymptotically. You can never actually get there because of energy reasons and such. But there is also a physical way to look at this, and in the last dying minutes or so of the tutorial on Monday, I actually mentioned why this thing will not go faster than c. And that's time dilation. If you see somebody push a mass along, even if he does it with a constant force, the acceleration that the thing gets is time dilated. Acceleration means a certain amount, fixed amount of extra velocity in a certain amount of time, but a certain amount of time in your frame is time dilated. So it takes more seconds for you to see that guy give the mass an additional piece of velocity. So, you know that I'm not a big fan of the concept of relativistic mass. Well, the mass increases. No, it doesn't. The reason that it looks as if the thing doesn't want to accelerate anymore is not because the mass has increased, but it's because you're looking at the time-dilated acceleration. Anyway, now, we left open, as a mathematical exercise, that this thing is a solution. Now, again, I'm never going to ask you, because it's simply not the course for that, But I'm never going to ask you, here's the differential equation show me what the solution is. But here we have a situation where I give you the solution. Let's check whether this is a solution. Involuntary volunteer, because I'm not going to write it down.
I think I can do it.
Yes, actually. Let's go for you.
Take one for the team.
Take one for the team. As if it's a bad thing that you have to stand here and talk to people. I do this all the time, okay? There's worse things in life.
I mean, I tried to do it the other day, but the thing is, I didn't get to f equals f, so I want to do it to know if I messed somewhere.
Okay, but we have a huge amount of high IQ people here, so we should be able to figure this out, okay?
Okay.
So don't look at me, I'm going to be silent for the next 10 minutes or so.
Okay, so that's the equation, and that should be gamma cube m dv dt. So, okay, this is 1 over 1 minus vc squared to the power of 3, if I'm correct. And then we can do the derivation of all this stuff here. So these two things, this quotient here is constant, so we can put it out. Squared 1 over 2. This goes away. Okay. That's going to be f divided by 1 minus 1 over c squared, and then we can substitute the v here.
For 1 minus v over c squared over to the power of 3, isn't it supposed to be 3 over 2?
Yeah, 3 over 2, yeah. Yeah, there you go. That's where no, actually I have it in my notes. Yeah, okay.
Again, lots of high IQ people here, we should be able to figure this out.
1 over f t divided by, that's going to be, wait, I'm lost. Yeah, 1 plus ft divided by mc, again squared, 1 over 2, and all these square brackets, just in case I don't want to be confused. This is also squared. This is 3 divided by 2. So let's just put here a square root to be more clear. Then we need to derive this thing. That will be the derivative of this one first, which is 1 times the second one. 1 plus ft divided by cm squared minus t times the derivative of that thing, which is going to be 2f squared t divided by c squared m squared divided by 2 times 1 plus ftcm squared. Okay.
Just your first term?
Yeah.
Is it already derived or?
No,
is
no,
it
no.
just
Do you mean this one?
the f thing?
That one.
Is
You
it
know-
already
you know
the
it's derived.
derivation of?
What do you
No.
Is it just a? Did you just replace?
replace the v by v with the expression here?
Okay. Yeah. Okay.
Okay.
Just,
So you've taken your f, which is gamma to the 3 times ma. You notice that gamma is a function of v, of course, and you just substitute our proposed v into the gamma to the 3. That's the first factor, the big one with the square brackets.
Yeah.
And then you still have to multiply it with the derivative of t over 1 plus something something to the 3 seconds or so, whatever. To the 1/2. Yeah, okay. Alright, so still going, you're now doing the derivative, yeah?
Yeah.
Okay.
Okay, so
Oh, that's a
this
huge expression.
v squared now, and that's going to be 1 plus ft scm squared. Just that thing. Continue here. Got
And all of this has to boil down to just f.
it. Yeah.
Okay.
Oh, wait a sec, please. So, okay, this thing here, I think, can be simplified if we just do one. Okay.
Everybody, please check him as he goes along. Yes.
C squared. All this is a squared, so it should be squared t squared divided by m squared, and then 1 plus ft divided by mc squared. Just going to continue with this expression here.
Just the first factor. The first.
Yeah.
Okay. While we're getting lost in algebra, can I remind everybody that this is the simplest case that you can work with?
Yeah.
Don't we have computers for this usually?
Sorry?
Don't we like use computers?
Yeah, you usually do this numerically, that you say, oh, let the computer calculate on every microsecond what the outcome should be, and then it will plot it for you. But even a computer will have a hard time to find the analytical expression for this.
Can computer find analytical expression of the thing if we don't have already like a method? Like
Yeah. There's very powerful computer programs. Wolfram Mathematica is a very famous example. Gives you analytical expressions, sometimes even for nonlinear differential equations, but certainly not always. Okay, so you're just cleaning up the first factor here, yes?
Mm-hmm.
Okay. Mm-hmm. Oh, Jesus.
Why is something wrong? Or is
No,
It's fine. It's just
is it like the way I'm doing it?
No. It has nothing to do with you. It has to do with the crappiness of the calculation, not the way that you do it. The fact that the whole thing itself is inherently crappy.
Especially.
Yeah, there is no beautiful.
No. Oh yeah. What? No, this is not correct. I'm sure there is a way to simplify this into expression like 1 minus something.
And if we try only to derive Vt to see if then we can have a.
Oh wait. It could be 1.
Mm-hmm.
Wait. FTMC. Is this correct? No. Could be that thing.
No.
minus?
C squared.
Is
It is correct.
Nee,
Yeah, I think it's correct. Yes.
Okay.
Oh, okay, but now.
That's only the
Okay.
first.
Yeah.
now I only need to do this part here.
Whew.
So I think I can take this square root here as a common denominator of this numerator here, which means that eventually here we will have this to the power of 3/2.
I agree with that.
So can you repeat that? What did you say?
So if I take as you have here an expression that you can simplify by putting everything
Okay, yeah.
with this as a
Yeah.
denominator,
Yeah.
and then it will, if you multiply this by that thing, then it will get
Yeah.
it will be like that to the power of 3/2.
Gotcha.
Yeah.
Okay. F squared
Oh, but I see beautiful things happening already.
t
Okay.
squared.
Good.
Good work. Ft divided by 3 squared.
this is great. I think it's time to whip out the old red marker of cancellation.
Okay, wait a sec. That's going to be, oh yeah, there you go.
There you go. All right. Okay, all solved.
Yeah, so cancel out. I'm gonna use the rectangle.
Yes.
That's a relief actually. So we have this thing here. Wait, that thing. Then we have on one side. So F equals. Yeah, I wanted to use it to
Okay. That works out beautifully. So, okay. So
In the end.
So when you did it at home, you said that you ran into a problem. Was it? Just
yeah, but the thing is, at some point in my calculation, I just didn't put the 3 over 2.
I see. Yeah, okay, that makes a lot of difference. And the crappy thing is, you won't spot it just by units alone. Usually you know that you made a mistake somewhere because the units do not fit anymore. But this has no unit, right?
Yeah.
1 plus something, something, something. So you can do it to whatever power and you won't find it in missing units. So that is a very easy mistake to make. That is very true. But this works out beautifully, yeah?
Yeah. Impressed.
Suppose doing the other way around, yeah? Just to make that point one more time, because it never gave you this. The checking already takes time, let alone finding it. So, okay, but there we go. So we fully understand this. We know where this came from. For the simplest case, we know that this came out. We saw that physically means that no matter how much pushing you do, you never exceed the speed of light. We also understand physically why that happens. It's the time dilation. The same amount of extra velocity starts to take an infinite amount of time if you go faster and faster, and therefore you reach some limiting value, and then the math tells us the limiting value is c. And that is a solution that's now been beautifully proven on the board. So this is a full worked exercise now. So great, thank you. Now, we have a couple of Minkowski exercises to do still. But if possible, it would also be nice if we can actually prove the principle of minimal action. Right? I mean, well, not the principle itself per se, but you know that nature chooses the path that makes the action come out either the smallest or biggest number, depending on what overall constant you put there with the minus sign or not. And then I just told you that if you want to make this thing S equals LBT, if you want to maximize or minimize it, that is equivalent to saying that this should be true, right? This is what we've been using all along. Now, I haven't proven that this is the case, it's just a mathematical exercise, but would you be interested in seeing how that works before we go into the Minkowski ones?
Yeah.
Yeah. I think it's worthwhile to go through this, at least once in your life, and then you can forget it for the rest of your life.
The derivation is in which theorem?
In which theorem? What do you mean?
Yeah, like who was the first one to derive the right hand side out of the first?
Oh, Lagrange.
Ah, okay.
Lagrange. As I say in French. The guy was French. I think we should be allowed to say that. All right. Now, I sort of already gave you a hint on how to do that on Tuesday. And that is really, if you will, by basic calculus, just basic standard stuff. Suppose that you have an S, okay? And you have an S, it's defined as such, X, T, and Vt, integrated over T, so that will give you a number. And suppose that, I'm going to draw a little P here, and by XP and VP I mean the actual path that makes this thing minimal or maximal, yes? Mm-hmm. The one that obeys the principle of extremal action. Mm-hmm. So by definition, don't ask me what this path is, this is what I'm going to prove, but suppose that it is We call this xp. Then I know something immediately. Namely, that if I would calculate the action for an xp plus a little bit extra x, a different path. This is the actual path that nature will take. I don't know what it is yet, I'm going to find out. But I'm going to take this path plus a little bit extra path. This is just another way of saying a different path than the one that nature decides to follow. Yes?
Mm-hmm.
We all see this, yes? This just means a different path than the one that nature wants. Same thing here. That means that the velocity will also be some other velocity that nature wants. Let me tell you first what the methodology is, and then we're going to actually work it out in detail, mathematical detail. In a moment I will show you that this will be the same as what I'm writing down now. That if you take the path that nature follows, and you're secretly going to look at the different path, so the path plus a little bit extra and the v plus a little bit extra, I will show you in a moment that you will get back the actual action of the path that is taken plus a little bit extra action. Now that shouldn't surprise you too much, right? Mm-hmm. Just in basic normal calculus, if you have fx, it gives you 4, and you then take fx plus a little bit extra, you will get 4 plus a little bit extra. Mm-hmm. Agreed? That's what I'm saying here. You take your path, you do a little bit extra, so you get your action back plus a little bit extra. Now, how this exactly works from here to here, and what this delta s, this little bit extra on top of your action will be, I will show you in a moment. But, just to show you the methodology first, I know one thing about delta s.
It must be equal to 0.
It must be equal to 0. Do you agree with this? It's very important that you do. Why should it be 0?
Because the s we already have with xp is the optimal one, so the smallest possible. So if we add something, or the biggest, like an extra one, so if we add something, it must not change the value. So
yes. Again, going to basic calculus. Let's go back to high school for a moment. If you have your optimal value, that will be your xp. It's a little bit different here because here xp are numbers, right, in normal calculus, and here xp itself is a function, but the idea is the same thing. Basic high school physics, if you have your optimal of a thing, or if you want the minimal, we'll just stick to the optimal for a moment, and you know that xp is going to be the one that has the highest value, then I know that going a little bit next to xp should give you a horizontal tangent, right? If there's one thing that defines the optimum or the minimum of a function, it's that its tangent is a straight line. How do I get a straight line? Well, for a straight line I need 2 points very close to each other and see if there's a slope in there. So I'm going to take x plus a little bit amount extra, going to draw a line in between, that gives you your tangent, your slope line, dartje afgeleide, and that tells you if this is 0, it has no slope, it means your original xp was the maximum or the minimum.
Is it? And if we have a local, like,
so
yeah.
Okay, so it's a local maximum versus a global one, because there might be a global one here. This one is silent and doesn't tell you which one it is.
Okay.
But Gideon, then are you considering that delta is like infinitesimal change?
Yes.
Okay.
Because if we're going to take a big amount, right?
Yeah, then
big delta, then my slope, it's a correct slope, but it doesn't tell you anything about the maximumness or the minimumness.
Okay. But the principle of minimal action is for the global or for the minimal?
It's silent on that. It just tells you that if you have found a path, it will be a minimum or a maximum. It doesn't tell you if it's minimal, whether it's a local one or a global one.
Okay, just tell you that the require thing is at least to be okay.
But that leads to something interesting, doesn't it? That we haven't really discussed. And I'm going off on a tangent here. That works on many levels. This comment now. But suppose that you do have an action of which a value, depending on its path, also has another maximum or minimum. Mm-hmm. You're going to do the principle of minimal action, so you're going to do this equation that we found, this Euler-Lagrange equation, that gives you a path. Is it the path that corresponds to this one or to that one? And they're in general going to be different paths. Mm-hmm. Now, how do you know if you have the correct one? And the answer is, just based on the Euler-Lagrange equation, you can't tell. Mm-hmm. Now, quantum physicists, who use this all the time, actually came up with a very good way to work with this. They found that nature doesn't have a preference for one or the other, or has a preference for one or the other, because both of them will have a certain amount of energy, right? If you have a Lagrangian with a certain value there, it corresponds to an energy. We did these calculations. This has an energy, but this global one might also have an energy. And then they say, well, nature wants to have the one with the smallest energy. So even if nature decides to start out here, it will at some point
reach the
other one. Now, in classical mechanics, it will be impossible, because if you're already at the top,
they go back in time.
No, it's not. No, this is not a time axis.
Oh, it is so. Yeah.
No, in classical physics, if you have a certain path, the path is crisp. Agreed? The path is very specifically located. This path that corresponds to the global maximum is very well defined. You know exactly, with no uncertainty, what that path is. It might be difficult to find it in practice, but nature has chosen a very definitive, crisp path. And, well, you know that if you're going to balance a little ball on top of a hill, and you don't give it any pushes left or right, because nature has decided that it's exactly there, it will just stay there indefinitely, and you will always stay here. But quantum mechanics tells you, no, paths are not crisp. So it's here-ish, plus or minus uncertainty relation by Heisenberg. But that means at the moment that Heisenberg gives a little push left or right, it will then end up in the next one.
Oh, is it because of the way we define also the Lagrangian as a equal to 0? So we use like a derivative. So like since we use a small like step.
This one, yeah.
This step, is it because we define it as equal to 0 when it's tend to be very small?
Yes.
And because we need that step, it means that it can be on both. We don't know on which side we took that thing.
Yes.
It can be on that side and on that side, and then we know that it must be around the small interval.
Yes.
Okay.
Exactly.
And then from the small interval, each like possible value has a different path.
Yes.
Like.
Agreed. That's
okay.
correct.
But
now going back to quantum mechanics just for a moment, and now going back to the actual calculation, because we're not doing quantum mechanics here, but you know it's so nice to connect these things to each other. But so again, this global maximum here in classical physics will be extremely crisp defined, no uncertainty. And that means that if nature has decided between these two maxima to choose this one, don't ask me why, but suppose that it chose this one, in classical physics it would stay here. The only way for this thing to not stay here is at the moment that you give it that Heisenberg uncertainty relation gives it a little push left or right. That means it's an unstable situation, as you can tell, yes. Right? Try to balance a pencil on its pin. It's going to be difficult. Classically, mechanically, it is possible. It's going to be extremely difficult. But in quantum mechanics, it's simply impossible, because if you would put the thing on its tip, even if you have a perfect situation with no drafts and everything, it just stays there, stays there, stays there, stays there. Quantum mechanics itself will give it a little push left or right because of uncertainty relationship of Heisenberg, and it will drop down. Here, it might also drop down. If it drops down here, then it looks for the next minimum or maximum that it finds, which would be this one.
But why not the local minimum?
No, it could also be this one. I very much agree. Yes, I skipped that one.
But also because the local maximum is still a metastable equilibrium, while the minimum is
yes, thank you for introducing that word. That's what I was looking for, metastable. This one would be stable.
Yeah.
Yes. Now, long story short, quantum mechanics tells you that even if you start out at the global minimum, you have a very high probability of the thing at some point deciding to go to another minimum, or another maximum, another extremized point. And that's exactly what you see in nature. That you have situations where nature started out choosing this path, and without any particular pinpointable cause, it will end up in another path that it will follow from that moment on. That's because of Heisenberg.
In classical, so there is no way to know, we just have to try numerically and experimentally and see if it works.
Okay. Exactly. Now, fortunately, usually there is only one minimum or maximum for your classical physics problems. Now, moving on for now, because we were going through the calculation, the point that we wanted to make here was that if you are in a minimum or a maximum, and let's skip the question whether it's a local or a global one, because the derivation will hold for both, then you know that the delta S part must be 0, because otherwise you will not get a tangent, a horizontal tangent, and which you require by definition of having found a minimum or a maximum. So the only thing that we have to do is state that this thing is 0. By definition, we'll for maximum or minimum, and then look for the path that makes this 0. That's the idea. Now, let's do that right here, right now. Make some space here. Now, in order to do this project, you need to know, of course, what delta S is, yes? Now, that is not too difficult. So let's start with our L of the path plus a little bit extra. So that's L as a function of xp. I'm not going to write it depends on t part, it's too much writing for me now. So it's implicitly, I mean, both of these depend on time. There you go. Now, because delta x and delta v are very small numbers, right? Because the whole idea is you want to have a horizontal line, but you have to take the horizontal line of two infinitely separated points. So you know that delta x and delta v are going to be ridiculously small. That means that you can make a Taylor series of this L. You know how Taylor series work, yes?
Yeah.
Now, Taylor series tell you that you have to take the function and pretend that this is 0, both of them. That's the first term. Plus the derivative of this thing times how much it is not 0. That's a Taylor series. If you don't know what I'm talking about, well, then the only thing I could say, you should know what I'm talking about. It's Taylor series. No, really, seriously. I mean, fx, classical physics again, classical just basic calculus. If you want to know what the value is of x around the point x0, you put x0 plus the derivative of f with respect to x. In that you put x is x0 times how much x0 and x are different from each other. That's a Taylor series, first order. And this is correct if delta x is very, very small. The smaller this is, the better it works. We're going to use that here. So we're going to substitute the x as if delta x is 0. Well, that just gives you xp. We're also going to put as if delta v is 0, that will give you vp. So the first term is this. That will be this part. Plus the derivative of L with respect to xp times how much xp and x differ from each other. Delta x. This thing is that thing. But I'm not quite done yet.
Yeah, for v.
I have to do the same thing for v. Because L also has v a little bit different. You get this?
And do you derive it with respect to VP or just V and then evaluate it at VP?
It boils down to the same thing if you write it down mathematically.
Okay.
So what I really do is I take the derivative with respect to x, and then I substitute delta x is 0.
Okay.
But x with delta x is 0 is xp, yes? So this is fully correct.
Okay.
Now, this is just the Lagrangian Taylor series. I don't have to write down the second order and the third order and fourth order because it's infinitely small. I'm going to take the smallest amount of difference, and then the delta x squared, delta x to the 3, 4, etc. are ridiculously small. You can drop those altogether. Now I have now how to rewrite, this part. Remember that originally it said here Vp plus delta V and such, and I have to integrate it over time. So I still have to integrate this thing over time to get the corresponding action. So integrate this over time, integrate this over time, integrate this over time. Do you see that this whole thing is really just the original action, this one?
Yeah.
And that whatever then remains must be what I call delta S before. So this will be delta S. So what is delta S? Just by reading off. If this is S, the rest must be delta S. Delta S apparently is equal to dl dxp delta x plus dl dvp delta v. Okay? Now this must be 0, otherwise xp was never a maximum or minimum to begin with. So this must be 0. If I find what my xp and vp are to make it 0, then I know, because I built up my argument that way, that the xp and vp are the actual path that minimizes or maximizes the action. So I'm going to continue with this part now. I have to erase this, so I'm not going to need it anymore, so let me continue here. So we have this thing, delta S, just copying the line for overview's sake. This must be 0. This is why I put the exclamation point over there, because we have to make sure that this is 0. My claim is, if you work this out, this will give you the Euler-Lagrange equation. And it already sort of looks like it, doesn't it? There is already a dl dx in there. So, yeah. Here's the idea. What if I'm able to rewrite this term in terms of dx? I mean, I can, right? I mean, if I play around with calculus and integrals and such, I can write this as a dx thing. If so, then I can take a dx out of the brackets. And by an argument that I will tell you when we get there, then everything that's within the brackets has to be 0 in order for the whole integral to be 0. And that thing will be the Euler-Lagrange equation. So here's the plan. I'm going to rewrite this part in such a way that it will give me something that has a dx there. So I'm just going to focus on this for a moment. dl, dv, and dv integrate over time. I want to make this into something that looks like this. Suggestions? It's not a physics question, it's a mathematics question.
V, could we write V as
chain rule?
Yeah, or as dx over dt? So it will be sigma. Yeah, this one. So at least we'll have at least one f.
Okay. I hear you didn't mention it, but the methodology that you propose is partial integration. Now, I don't know how you remember your partial integration rule. I always write it like this. F times g integrated is the same as f capital G minus g small f, where small f is the derivative of big F and small g is the derivative of big G. This is just a rule from calculus. You can easily prove this for yourself if you know how differentiation works. I'm going to apply that here because I have something here. I have a dv, and I don't want dv, I want its antiderivative, right? I want to turn it into a dx. So I have to integrate my, I have to take the antiderivative of my v. So if I now just call this thing correspond to this g here, then this rule says it should give me back big G, which is going to be delta x. So by just looking at this rule and wanting to have a delta x as an overall thing, I see, well, then I have to call my delta v, I have to call small g because it will give me big G, delta x. Now then this part must be big F, and now I'm going to apply the rule. Partial integration tells you that the first thing you get is f and g without an integral sign. So capital F, now capital F is just this, dl dvp, times capital delta v, which is delta x.
Yeah.
Fine. Minus, I'm over here now, capital G, that is exactly the delta x I was looking for, times the derivative of what I called f here. What derivative, by the way? There's time derivative, space derivative, which one is it?
Time.
It's time, yeah, I mean it's this one, right? So this must be d dt dl dvp. No physics here, just mathematics. And I have succeeded in what I wanted. I wanted to write this thing as something that has a delta x, and I have that now. But unfortunately I also carry around this baggage. Claim this is 0 by itself. And I'll let you think about that, why that is for a moment. Supposing that this is 0, again, think about it for a moment why you think that that is, but it is. I'm going to continue here, then I find that my delta s is integral. This thing I kept as it was. This thing I've replaced by all of this, with this thing being 0. So what remains is ddt dl dvp delta x integrated over time. This is what I wanted. I wanted a delta x here and a delta x there. Why? Because I can now take it out. And remember, this has to be 0. Now tell me one way that you can make this 0. Right? It has to be 0 because then you get your maximum, your optimal path. The path that makes you
of the integral is 0 as well.
You can certainly make this come out 0 if you make sure that this is 0 always, yes?
Or constant.
But what if this? But the inside, the inside of the integral is 0, then would it not be a constant or? But no, sorry.
If this is 0 inside the integral, then the outcome of the integral is just going to be 0. So, now let's go with that option, and you get that apparently your path is going to be a maximum or a minimum if this is true. And that's the Lagrange equation we've been using so by this time.
Just to came back at the first argument, that dl over vp times
This
is 0.
Yeah, there's two subtleties here. One of them is I assumed that this was 0 by itself, and I gave you a moment to think about that. There's a second.
Maybe it's because we multiply two different things now, like delta x with delta vp. Normally it's, I don't know if...
Well, you can make this 0. I mean, it's a product, right? It's something times something else. So it's certainly going to be 0 if one of them is going to be 0.
Yeah.
But that's certainly not always the case, because if delta x is 0, then that means you were never looking at a different path to begin with. It's hard to take a derivative if you're not going to look at a different point. So delta x is certainly not 0, but dl dvp is what we call momentum. That's always not always 0. So something is going on here.
Is it because of the definition of vp, which is the tangent of delta x, kind of? So we have, like, if we have a linear, what is called, like a scalar product, we'll always have like 0 since it's supposed to be tangent to, no.
Orthogonal?
Yeah, to the x. Since v is like its derivative.
Well, I don't see how inner product would help us here. Inner product would tell you something about vectors. These are not vectors, they're all scalars.
Oh, okay.
And for scalars, a product of two things to have the outcome 0,
yeah, but if
one of the two has to be 0.
If I plot the graph in terms of v on one scale and x on one scale, one is on v, there is no factor of v in delta x, so multiply a factor with no delta v with a factor where there is a delta v but no delta x.
I understand what you're trying to do.
I don't know if it's...
No, that doesn't work, because what you're trying to do, you're trying to read this as a vector and read this as a vector. You, in fact, with your gestures, you already made a vector space out of this with your hands, right? You say, oh, well, this axis, and then the inner product has to be 0, or
but
it might be 0.
But if we just turn only in things of like only like multivariable, not only just...
Yeah, but it isn't. I mean, your whole argument it has the premise that this is a vector and this is a vector. You cannot take inner products of non-vectors. So you're assuming that it's a vector, and then you sort of work your way towards that the inner product has to be 0. These are not vectors, they're scalars. They don't have an inner product, and it's certainly not 0. There's a subtlety there, though. Does anyone have an idea? If you don't, I can fully imagine, because it's a subtle argument, but it is there. Let me give you a small hint. An integration you take from some moment in time to some other moment in time, yes?
Mm-hmm.
So 1 moment in time, some other moment in time. 1 moment in time, some other moment in time. Moment in time, some other moment in time. Moment in time, some other moment in time. I write I for initial moment and F for final moment. Then the rule of partial integration tells you that you have to take this product, calculate what its value is at the final time, calculate what its value is at the initial time, and then subtract them from each other. Now that is going to be 0, and you have to understand why.
The path will stay.
If I give you a physics problem, and I tell you how a mass is moving,
oh yeah,
it's always, you always start out by saying, here's a particle at my initial moment, yes?
It's because it's the same at every time. We have the same pathway at every time. No matter the time we will get, if we use a different, no matter if we use a different like time set from a TF or TW, the path, the structure of the path will always be the same. So it doesn't matter if we change it won't depend on x. Like the x will always be the same at TF and at T1. The delta small sigma.
Yeah, but no, that is true. But why is that? Is this for every moment in time or only Ti and Tf?
It's for every moment in time.
But then you're not looking. Then the thing is not moving. If x is going to be the same value at any moment in time, then you're saying that the thing doesn't move.
No. Between the.
Let me go back to this example. If I look at just basic question in physics, would be something along the lines of at some moment in time, its position is 4. Okay, question is, where does it end up? Agreed? So at some point in the future, Tf, it will end up maybe at number 6. Now, there's the whole thing that Lagrangian physics tells you is how it goes from this point to that point. There is some path depending on physics and forces and potential energies. This is the path that physics actually takes. I just randomly drew a path. Suppose that it was this path. The path that it does not take is this path. Agreed? It takes this path xp, and this will be your xp plus a little bit extra. Well, it's more than a little bit, but you know, you get the idea. But one thing I do know,
the xp will
they will start at the same point and it will end at the same point. Right? Would it be a strange way of doing physics if I tell you, well, the particle starts at position 4, calculate what it does in the future?
So we don't look at the path, we only look at the destination. Since the destination are the same,
the beginning point and destination are the same, because these in physics you call the boundary conditions. You tell your initial conditions. You tell the person who's going to do the physics how the situation starts. There is no delta x at your beginning position. There's also delta x at your end position. The way in between is what you don't know, but you do know how your system starts and you don't know how it ends.
But if the path doesn't matter, then it means that the force is like kind of.
No, the path matters. What I'm saying is, the beginning point is the same for both paths. The end point is the same for both paths. In between, the paths are certainly not the same. But the paths will meet, the correct path and the path that nature does not take, they will meet at the beginning point and the end point. Another way of saying exactly the same thing is that delta x, remember it was a time-dependent function, is always some number, yes? It will be this number, how much the actual path and the path that you're looking at, they differ from each other, but at the initial time is when delta x is 0. The final is also going to be 0. Please make sure that you understand what I'm saying here. You don't know which of these paths nature will take. Well, I call this one the one that it's going to take, but you don't know which of the two it will take. But one thing that you do know, the path nature takes and the path that nature does not take will start at the same point and will end at the same point. That's another way of saying that your delta x, which is the difference between the actual path and the path nature does not follow, is in principle not 0, except for the beginning point and the end point. Going back here, so for partial integration tells you have to put in where the initial time and the final time. Now look at this. Delta x, you have to calculate first its initial time, that will make delta x 0, and its final time will make delta x 0, and subtract them. 0. Now any point in between these two delta x is not 0, but at these points it is 0, so their difference is also going to be 0. This is why this is 0. So that's not the mathematical reason, that's a physical reason. The physical reason is you know what your initial state of your nature is that you're looking at. Now, therefore this is 0, then the rest follows. One more subtlety, I was waiting for somebody to make a comment here. Right, so this is now solved, we get here, and then we said, well, this whole thing has to be 0, and I say, well, the only way that this can be completely 0 is the thing in between is 0. That's certainly true. If this is 0, or your Lagrange, then the integral will be 0. Who sees the subtlety there?
Yeah, what about delta x?
Yeah.
Well, I mean, if this is 0, then delta x can be whatever, right?
Yeah, but
0.
can we say that is gonna be 0 since we start from the notion that it's gonna that delta s will be 0? Can we say delta s can be 0 if delta x is 0?
Sure. One possibility is that you say delta s will or delta x itself is always 0 for any moment in time. Then sure, this will also be 0. That doesn't surprise me though, because saying that your delta x is 0 to make this 0 just means that you, let's see here, nope. Remember that you got your delta s by saying that you are not at your optimal path, not the path that nature takes. But if you're going to say that delta x is 0, that's just the same thing as saying that you are already at the, then obviously delta s is going to be 0. So it's sort of a tautology, right?
A combination of delta t and delta x that would be equal to 0, although both
that's certainly not true, because this thing, by definition of integration, will take all values between ti and tf, and it's a sum of these things that by principle is going to be 0, by definition of what an integration is. Now the subtlety, so there's two options. Either this is 0 and this is whatever, or this is 0 and this is whatever. But the second thing doesn't give you, I mean, that doesn't give you any new physics. It just tells you I'm already at at the path that nature is trying to take. But maybe a combination of these things. Maybe this is not 0 and this is not 0.
But together,
together, the sum of these things happens to add up to 0, right? Is that possible?
So the extra time.
It means that the sum, but if you multiply two number and you find 0, it's not normal unless you have no.
But oh, wait a minute. This is not one multiplication, right? An integral is you take this thing.
Yeah, but I mean for dx.
So if you
delta x is it's a multiplication, no?
Yes.
We multiply delta x by what is in the thing.
Yeah. But
so I'm thinking that if we multiply that terms by dx, it's just like if we just imagine in terms of number, it means that we have two number that multiply by themselves as 0, and we put a condition that one terms must not be equal to, that both terms must not be equal to 0. I cannot think of any real number that will give that kind of solution.
Oh, I can. It's an integration. An integration means take this whole thing, whatever it is, put in some number of time, you get a value. Then one moment later, you're going to take the same thing, put that moment of time in, you get a different number, you add these two numbers. An integration means take this whole big thing in the middle, calculate what its number is at any moment in time. You get all kinds of numbers in a row, all the numbers in between ti and tf, and add everything together and see what comes out.
Yeah, but in the end, what is important is that it's not dx, delta x that change, but because it will not change with time. Like no matter time, we said that at tf it will also be 0, and at t.
Yeah, but it will change in time. Look, I mean, at any moment in time, this is dx. Yes, the difference between the path that nature takes and some random other path. Now, at any moment in time, there will be a different number.
Okay. So it still depends.
So you have to add all kinds of numbers here. For any moment in between ti and tf, this whole thing in the middle will give you a number, and you have to add all these numbers. Now, do you agree with me that if you have many numbers that you add together, then that outcome might in principle be 0? Right? If you have 3 plus minus 2 plus minus 1, none of these numbers a piece are 0, but their sum is 0. Dus there is a possibility that this thing, not this thing by itself at any moment in time is 0, but their sum is. And my point is, no, but that will not happen here. Again, there's a subtlety there, right? That's what we're talking about.
Oh, does it mean that it switched of path? Because the path is like already decided. So if it's
this path is not decided.
No, but this is not decided. But if the overall thing is 0, doesn't it mean that we are in the same path at the same moment as the optimal one?
No, but now you're working backwards. Now you're saying you're already assuming that we are on the optimal path.
Yeah, but I'm saying if I look at the non-optimal path, and I say, okay, the integral of that is equal to 0, could we say that at this particular point it means that it must be the same as the...
No. No, I mean, at any moment in time, delta x, except for the beginning point and the end point, there will be a delta x equal to non-zero.
Yeah, but what I mean is, like, what is the meaning of the integral, just in terms of when we draw the thing?
You take... Here's a moment next to ti. Then there's a difference between the actual path that nature takes and the path...
But I mean, if we have the whole thing, so delta x
times this.
Yes. What on the graph would it means, like, at t, for example, y?
That's what I'm saying here. At any moment, any next moment, the delta x will be this value, yes? The difference between the two paths, and then you still have to multiply whatever this number is by whatever this number is.
Yeah, what is whatever that number is on the graph?
You cannot show this thing on the graph.
That's what the question
is.
Like, to see if it can come...
It is some number, I agree, but it's not representable in the graph.
So maybe, does the solution like rely on the fact that, okay, I'm probably gonna say something really wrong, but the path, all of the path cancels out on one side and on the other side, except on the one on the line that connects.
Why do they cancel out?
I don't know, because one is going in...
So here's another path, yes?
Yeah, and then you can do the symmetrical one on the other side.
Yes, and they cancel each other out.
No? Okay.
They're infinite, right?
Yeah, but no, that's a good question. I mean, maybe for any path on one side, you get your delta x's and such, and you also get one at the other side, and maybe they cancel each other out.
Yeah.
If it was just delta x's, and you have to add these together, that will be true.
Okay.
But you have to multiply delta x with some number, and I'm not sure that on one side it will be the same number that you multiply your delta x with the other side.
So what again did we say that is that number? Like, what does that represent?
I cannot show this in a picture. This
no, but like not in a picture, but what does it? What is the meaning
physically
of it?
I have no direct physical interpretation for this.
Okay.
I mean, for me, the way that we built up this argument is that this thing appears as a mathematical consequence for forcing your path to be the optimal path. I have no better physical interpretation for this. I will give you a hint. I drew this other path here, this other delta x. What should the outcome of this integration be for this other path that you follow? Right? There's a different delta x here between the actual path and this new one, right? It's a different delta x and this one. What should the answer of this integration be for that red path that I drew? It should be 0, right? For this one.
Yeah.
How about for the red one? Still 0?
0 too.
Still 0 because it's not the optimal path. How about the green one? Okay. Comes with its own little delta x. Okay.
Still not 0.
Should still the delta x should still.
Oh.
What should the delta s be for the green path?
0.
Still 0.
Yeah.
Every single path that is not this perfect nature has chosen path, this one, every other single path that I draw should give the answer 0 here. So no matter if my delta x is going to be this thing, the distance between the actual path and the black path, or this thing, the distance between the actual path and the red path, or this thing, the difference between the actual path and the green one, for all paths except for the actual path that nature has chosen, delta x will, in principle, itself not be 0, but should give this thing 0. So what I'm saying here is this. If I replace this delta x by the red delta x, or if I replace it by the green delta x, it should always be 0. Now, I can make any integration come out 0 by, well, choosing my delta x appropriately, right? Suppose that I do a calculation here, the answer is 4. I say, you know what, I'm going to just twiggle my delta x around in such a way that it will still become 0. Do you see what I mean? Any moment in time, you're going to choose your for any moment in time, these delta x's will be some number. It's going to be different numbers for the red and the green and the black. But still, you want the outcome always to be 0.
So will this be a constant difference or something like that?
But how do you multiply something and make it 0?
It's not. This thing itself is a sum of multiplications. It's not just one multiplication.
Yeah.
Integration says you have to sum many multiplications. Now, let's be. Maybe it's a little bit too abstract the way that I'm asking now. Okay. Suppose, do you all see that this is a product that you then have to sum? Suppose that it looks like this. Now let's do it here. Suppose that I am now going to write. Suppose, for a very simple case, there's only 2 terms, the sum of 2 things, but every 2 of these terms is a product, yes?
Yeah.
Yes.
Oh, we have a condition on the plus maybe? So we know something
No,
that at one point...
plus is definition of the
Yeah, but that at one point 1 must be negative and no.
Okay, that's true.
Yeah, but
Very
that's still
good.
0.
Suppose that there is a rule in nature that it must be 0. Now this is not 0. I can make it 0 though. I say, you know what? 4 times 3, that's 12. Here's a 2 times 7. But I can, if I replace this by minus 6, then it will still be 0, right?
Yeah.
So I can fiddle around with the delta x's at any moment in time to make sure that the sum of all these contributions will add up to 0. Do you agree with that? That's mathematically possible.
But do we know that there is only one solution, or that it's possible for every possible?
You're exactly right here. Do you remember the point here that the outcome should be 0 regardless of what your delta x's are? Do you agree with that thing?
Yeah.
Do you agree with me that that means that you are not free to randomly change your 7s to minus 6, because it should work for every numbers that you put here?
Yeah.
Yes?
Yeah.
If you want this sum, the sum of products, to be 0 always, but you're not allowed to fiddle your delta x's to make it come out 0, then there's only one way to make it come out 0, and that's to make sure that not the 6 and the 3 are fiddled such that the outcome is 0. You have to make sure that the 2 and the 4 by themselves are always 0. You have to make sure that this thing is always 0. Only under that condition you will get for every single path, with no specific fiddling to make it come out 0. No, it should come out 0 for all paths. The only way to make that work for every single possible delta x as a function of t is to make sure that the thing in front is 0.
That's what we started before. We only
Yeah.
said that
We
that was
yes,
0.
Yes, but then I said there's a subtlety. I said, well, we can make it 0 by saying that the thing in the middle is 0.
Yeah.
And then I was expecting somebody, I'm not going to name any names, but I was expecting somebody here to say, but wait a minute, there's another way to make this 0. And the other way of making this 0 is by fiddling your delta x's in a particular way. And my point here is, but you're not allowed to fiddle your delta x's, because it should hold for every delta x. For every unfiddled delta x, it should also hold.
Okay.
And as a result, this must be 0. Long story short.
So we cannot change delta x to fiddle the thing, since no matter what happens, it must be...
I'm sure there is one delta x here somewhere, for which it happens to come out 0.
Yes.
But it has to be true for all delta
Yeah,
x's.
so we cannot...
For unfiddled ones as well.
Okay.
And the only thing to make that work is to make sure that the thing in front is always 0.
Yeah.
So that was the subtlety that somebody I was expecting to say, a very specific person, but I'm not naming, okay? It's meant as a compliment though. Now, long story short, the whole thing that we built up was, we want to make sure that the path plus a little bit extra is going to give you a delta s of 0, because that is by definition of a maximum. Then we looked for, okay, when is that the case? And we found that the only way that that is the case for every single path in nature does not follow is to make sure that Lagrangian obeys this equation. And that's the one that we've been using, this Euler-Lagrange equation. This is the one that gave us gamma to the 3 m times a equals f and such. So, you've seen this once. If you're going to continue in physics, you will see this many more, not the derivation, but this rule. So I think you should have seen this at least once in your life. Okay, so how are we on time?
15 minutes left.
Yeah.
50?
50.
Okay, because I would like to do some Minkowskis still. Need a 10-minute break or so? Yeah. Maybe do some Minkowskis? Right. So, we have some Minkowski exercises left. Unfortunately, we are again in the crappy logistical situation where I cannot be in it, so I decided to do it as follows. I would like to make this interactive. So, I am on the board going to draw as well as I can, which is not very well, a Minkowski diagram. It's going to be so crappy that certainly do not trust what you see on the board, as in the events are at the right place and such, hopefully, if we communicate well. But the board will not be very good for you to actually read off the numbers, right? It's just too inaccurate the way they're going to draw this. So, my plan is as follows. Here's your stack of Minkowski space-time paper. And my idea is to do it as follows. We'll go through an exercise where I, on my crappy board in discussion with you, are going to pinpoint where things are and how we're going to do things. And then you, on your paper, can actually measure off what the correct numbers are. Is that a good idea? Yeah. Now, we started doing this at the end of last tutorial, but it got sort of lost in the messiness of the last 20 minutes when everybody was tired, including myself. So, we might want to go back to 6-7, or we can immediately skip to 6-11. I'm happy with both. Preference? 6-7 is a relatively short exercise. We can quickly go through this. Maybe it's a good idea to do this. Okay, let's go through 6-7 again. So again, as a sort of discussion with all of us, we're going to ping-pong on the board where the lines and the projections are going to be, and then you on your pictures can see what the numbers are. We are going to need for this one a Minkowski graph paper that corresponds to 3/5 of C. So here's your stack. Find your 3/5 of C, please. You know, there's not enough for everybody, right? So you have to hold around. And if you want an actual version of this paper, go to Leo and you'll find it there.
They're all different, no?
Yeah.
Oh no, they're two sides.
Yes.
Oh no.
There is 3/5 of C, please.
Well, you can do that in trade.
Yeah, but then you can get the
at least I'll have the correct axis and I'll be.
True, yeah, but if it was at C, then it would just be this.
Isn't it there? No.
But I don't think it's close. Like it's
No, yes.
No, it's
yeah,
not.
this one.
No.
No.
0.3.
No.
Like here.
What the fuck?
Horrible.
Okay, so we
Be mindful that the microphone is recording this for live. So that means there's some parents at home who's going to watch this and think, wait a minute, that girl, that mouth. Somebody send her a piece of soap, please.
It's a matter of expression.
I know.
You
don't have to just.
No, I'm gonna justify it.
No, you don't have to justify it.
It's good because that means I'm not angry anymore after.
No. But you need the calibration hyperbole.
Gideon, it's a beautiful stack, but it's not in there.
Using the number
No,
of squares.
it's not.
Have you found a
It's no use, right?
no 3/5?
Nope.
Nobody.
Whenever you move,
Yeah.
Yeah.
whenever you move.
My question.
What do you mean?
I'm not sure I understand the question.
No,
mean?
her
It was my
question.
question. Once you continue, like, how do we calculate? Like, how do I know?
I don't know.
Yeah.
Now I get it. Okay. Whenever you move
Yeah.
across the extraction 5 steps, 3/5, yes?
Five
5 steps,
up.
then you go 3 up.
Then it's not.
You can show them.
Okay, fine.
Okay,
That's
see,
5,
okay.
3.5. Look at
Just how do you get again the stretching factor?
That's
I know it's thrown in
Wait,
the
I
thing,
have
but if you have to
something.
compute.
Yeah, I don't think I can do
Like,
that. You're right.
but
we're going to need
Yeah, he explained something else.
Yeah, but
It's definitely
we're just gonna do it on
one.
That's
Prime axis.
Is that
Okay, where's one, two,
No, but where did you find this?
And if it is the speed of light, it
There
would
we
just be
go.
1 line. Yeah. Okay, so
Like-
the
I
closest
just-
is now or the fastest.
Okay.
There, I don't like really small ones or really big ones.
That's like 2 weeks ago.
Is that the one?
Oh yeah, right. This is the one.
Yeah, this is the one.
Yeah. I just switched the experiment because it doesn't really matter.
Yeah.
You can
Okay.
Have everybody found it? Yeah.
Robin,
Is it the one from the previous group or so? Or
No, that's mine.
It's always the girls, huh?
okay.
always the girls.
Always the girls.
Always the
Okay,
girls.
let's see.
Us guys,
Not like
yeah.
we're gonna have them very diagrams. Can you also
Yeah,
like put
this is
diagrams on the
fine.
other
I
side?
just, you know,
Because-
what we did.
Because like I tried to do the
we
exercise,
said
can do,
7,
like,
6,
200.
7, but the diagrams only
Yeah,
go
yeah.
the positive
Oh,
side.
that happens. Yeah, yeah.
It makes
It just
more
means
sense.
the thing happened in the past.
Cheaper.
Because
Okay, guys.
is there.
How many of these the right Minkowski graphs have been found? There's one there. Is there one there as well?
She has it, but we.
Well, she has a solved version, so that means we have literally one
Yeah.
copy. Yeah. I mean, I printed 10 of these. Are you saying that the other group took 9?
Yeah,
Yeah.
definitely. Yeah, we know
We are
them.
saying
Okay,
no.
you can look
It's
them up
possible.
and leave them up later. Now, honestly,
We know the
this,
resonance of the
I
shape.
would
So
like
you
to
are
add
taking the
one more. Well, you have
measurements here,
thing
right?
there.
Yeah,
So
and
we can
here
pretend
you can do it
this
here
nose
as well
closed.
and then
Do I
project.
have
Yeah, no, we actually need a 3/5 if you want the actual
No, this one
numbers.
is
But we can do it on a different thing or change the speed.
So we can use
Oh, we can
some
change the
voice,
speed.
like-
Find the speed
That
that
would be
everyone
excellent.
has.
We could actually do that. We could actually change the exercise and this is what.
Like
That was
It is quite slow, huh?
It's on this one, it's so if this is 1000.
People, we have two options here. We're either going to do this with the 2 graph papers that we have about with 3/5 of C, or we just change the exercise altogether and just change the speed to such that we do have enough paper. Which of the two shall we do?
Whatever you want.
That is easy. Okay. Very passive.
I mean, numbers don't matter. We just want to see how it works. So.
Okay.
Or
Then
we do 6.11.
what is this? What is the speed of 6.11?
This here is
Um,
800.
There's a lot of 1/5, huh?
So
Yeah, there's
5000
another 1/5.
here is 800
1/5.
here,
Yeah, one.
6,
Yeah, there's
7,
another
8,000
Another
here.
1/5. We all have 1/5 here.
Okay, guys, let's go with 1/5. Okay.
Okay.
We're going to change the numbers in the exercise. Same methodology, different numbers.
Really? Pretty slow though.
Yeah, we don't have any good ones.
1/5.
That's
So
true.
5 is right and 1 is
You're right. But then again, best we can
it
do.
should be
Just don't forget to do that in the exams. Like,
Okay, I already
negative
drew this
values.
one though.
Don't worry.
So
Yeah, the rest we will get to the exam.
But I'm not
correspond to the
sorry.
exercise. Has everybody now 1/5 in front of you? Okay.
Oh, let's share some.
no, we do not.
Okay, but before you also claiming that there wasn't any fitness and then there was 5 numbers.
I didn't claim it yet.
So you,
do it.
Yeah, this is
Okay, good.
Okay.
Alright, people. The numbers are going to be different than the exercise states, but then again, what can we do? Please tell the other people that they shouldn't take 9 of these copies, alright? Next time. Well, there's no next time, but in general, give them an education and tell them that they shouldn't take everything.
I swear they're gonna get high grades.
There's, yeah, well, just based on this. Listen, again, we've already went through this, but I think it pays to go through this again. It says a spaceship of rest length 1,000 meters moves by us at speed v is 1/5 of c. It's 3/5 according to the exercise. Let's make it 1. Now, again, my drawing is certainly not on scale, but that's not the point. You have it on scale, so you can do the actual measurements. Now, I propose to first start by writing where the spaceship is. It says at t0, so that means in the origin, because that is t is 0, is when the nose of the spaceship passes us, and we are stationed at t0. So here's the nose of the spaceship. The dot that I'm drawing now is an event. It means the moment in time and space that the nose of the spaceship passes us. This is not all, because the ship has a rest length, 1,000 meters. Again, I don't have a scaling here, so I'm just going to randomly draw a thing there. That's another event. This is the event of where the back of the spaceship is at the moment that the front of the spaceship passes us. That's this. And the distance, actual amount of meters, is 1,000 meters. So I haven't done any physics yet. This is just me putting the information of the exercise in a Minkowski diagram. All right. Just as the nose of the ship reaches us, that's this event. What does the clock in the ship's tail read? Now, I found that it's sometimes somewhat a little ambiguous what it is that the exercise wants from you. not because the physics is ambiguous, but simply because sometimes you can read an exercise in two ways. Now, what this exercise states is, at the moment, that we, and when I say we, I'm always going to refer to the unprimed people, the non-spaceship people, that we look at where the back of the spaceship is. We are going to measure the back of the spaceship. Okay? Now, so let's start with pinpointing in our Minkowski space-time diagram where, when we are going to measure the back of the spaceship, where that event is, our measuring of the back of the spaceship. Where's that event? Where's that dot? I see you do a... I'm just not sure.
We just a project.
Yeah, is it straight up or is it this one up?
It's a projection. A straight projection.
Why is it straight?
Because it's in our reference frame, so
yes.
we need the same...
Agreed, and I made that mistake on Tuesday. Yeah. And you pointed that out to me.
Yeah, it's still the
yes,
borderline of
but
the...
yes, it's good, but it's good to talk about this. This is indeed a projection. It does tell you something. Okay, and I will tell you in a moment what that means. But this is not the one that the exercise wants you to draw. They want you to draw the one, and again, my drawing is going to be crappy, but the one parallel, the projection, on this one. So, this.
What?
Now, the question is, why does the exercise want you to draw that one? And in order to understand why that is, here's the nose of the ship, yes?
Yeah.
This line is not just the CT primed axis, it's also the world line of the nose of the ship. This is how the nose of the ship moves through space-time. Here's the tail end of the ship. How does it move through space-time?
Oh, the same
Parallel.
trajectory, same angle.
Same angle, right?
Yeah.
Yeah.
Multiple ways of seeing that. But I think the easiest way is that the distance between the world line of tail, the distance between this world line and this world line, the world lines of the nose and the ship, should be a constant. Because the ship stays at a fixed length, a fixed width. Do you agree?
Yeah.
So, what we have here now is how the tail of the ship moves. We haven't answered the question yet, because the question was, the situation was, that us, the people who are not moving along with the ship, are going to measure the length of the ship, where the back end of the ship is. Now, if there's one thing you should really have fixed in your mind right now, is that if you are going to measure a length of a thing that's moving by, you make sure that you measure the front and the back end at the same time. Agreed?
Yeah.
Okay. Now, if we're going to take this point as the back end point, that's not at the same time for us. For us, there's a difference in time. So that means that we will conclude we haven't measured the right distance. So what are we going to do? We are going to, forgive my imprecise terminology, we're going to wait until the tail of the ship, who moves through space-time along this line, crosses when we see it at the same time as the nose of the ship. This is why we need this projection. Now, I said I'm going to be careful in my phrasing because I say we wait until the thing gets there. Now, I hope you agree that once the tail of the ship is actually here, in our frame we haven't waited, yes? Yeah. By definition, we waited, it happened at the same time. So this is why the word waiting is easy to phrase, but it's not what I'm doing. So for lack of better terminology, I will say something along the lines of this. We're going to take the point along the world line of the tail of the ship that corresponds to the same time as the world line of the nose of the ship. Okay? So instead of waiting for, I'm going to say taking the point. So again, this is how the tail of the ship moves through space-time. And because we are measuring the front end and the back end of the ship, that means we take the point of this world line that in our frame is at the same time. Then we get this thing. Now we can immediately do some nice things here because we have now measured the front end and the back end at the same time in our frame. So that gives us a distance, right? How wide the ship is seen by us. Do you agree that that is this distance?
Yeah.
Okay. Now,
if we had switched the axis, yes, and we said that the CT prime is on that front and the arm, yes, then the projection will be straight.
That will be straight.
Okay.
Yes.
Okay. Because that's I switched the axis beforehand. That's why I was so confused when we.
I understand. Okay. Now, this is a matter of you taking your ruler, drawing, checking how many tick marks you have, and you can measure what this number is, yes?
Mm-hmm.
Now, if you know your Lorentz transforms, you can also calculate what it is. Just very quickly how you would do that. You're going to measure the distance between these two events. Okay, so that's your delta x. And you know by Lorentz transforms that delta x plus v delta t, something like this, but you're going to do this at the same time. So that has to be 0, yes?
Yeah.
Anyway. Or you can immediately switch to Lorentz contraction and just conclude it's going to be the shorter distance. Now, 1/5 for v gives you some value for gamma, and we've switched some numbers. I don't know what the number is, but you can easily figure that out. Or you can just measure a number. If you do your scaling correctly, you will get that out. Now,
so
that is all fine.
When do we use a straight line then?
Yeah, oh yeah, I would say that this projection also exists, but it means something else. If I'm going to take this straight line, this is the world line of where the back of the ship was. Okay? Now suppose that I take an exercise, it's where the back of the ship was, assuming that it does not move in the unprimed frame. Look, at any moment in time, it will be at the same x. So this line corresponds to a ship of which I bolted the back end to the floor. The nose keeps on going. It stretches out, and not because of time dilation or Lorentz contraction, but because the thing is elastic or something like that.
Yeah, but then the back of the ship becomes goes in our reference frame because it's
parallel to our axis.
It doesn't. Yeah, it's in our. It switches to our reference of frame. The back of the ship.
What do you mean it switches to our back of?
It stays in the same.
In our frame, it stays at the same location.
Yeah, so it's in our frame of reference. It's not anymore in the frame of reference.
I don't know what you mean by that statement. The ship is in both frames of reference is going to be somewhere. Yes.
Yeah, but so the front of the ship.
Yes.
Is not in our frame of reference, right?
It's a different. What you mean by that? Because the front of the ship is going to be somewhere in any frames of reference.
Yeah. Okay. Then how can I say it? Let's say it's a different observer.
Yes.
It measures length and time in a different way than we do.
I agree.
But if we do the stuff to B, what did you say that we
stuck?
That we stuck B. Then B switches, and it will not anymore measure time and length as the front, but it will measure time and length in the same way that we do.
Oh yeah.
Well, yes, yes, okay.
Because B is not moving, so
because
B should be
that means that B. Okay, now I understand.
So how do you say it? It's not in our frame of reference. What is the right terminology?
I wasn't teasing you. I really didn't understand for a moment what you meant, because of course the back end and the front end of the ship is going to be somewhere in everybody's frame.
Yeah.
Okay, but what you meant, I think, is it's going to be at rest in our frame.
Okay, that was the word.
It's not moving, so then it should be in this. B should be. Yeah, on here.
So this line would be in the case, and then you're right, in the case that I take the back end of my ship, I glue it to my frame, and I let the front end of the ship I let go, then you're right. I mean, the back end of the ship is going to be in my initial frame as far as the values is concerned.
Yeah, so now that I have the right terminology, I reformulate it.
Okay.
So, if we take the straight line, if B switches from being in the state, at rest with respect to the frame of reference of A to being at rest in our frame of reference.
Yes, that's correct. Okay. But do you see that we now completely changed
it's
the
a
physics
completely
of the
different
exercise?
thing. Yeah.
It's still a correct exercise, it's just a different exercise. So you would have some elastic ship of which the back end stays here, the front end moves forward and it stretches out or something.
The B shouldn't be on the X prime line, it should be on the X line. Because if the B is not moving, there is no speed.
No, but this thing has no speed. Do you agree? Along this line has no speed. It stays at the same position.
Yeah, with respect to us.
In time.
Yeah, but then the event should happen. For me, it shouldn't happen like in the X prime frame.
What event do you mean? Every point in this picture is an event.
So B, if we glue B.
Yes. B is glued to the floor.
Okay, yes, but I don't understand. For me, I don't understand why we put it in the prime frame along the prime frame, since it's not moving along with the prime frame. So B should be on the X axis.
You can choose.
And A should be on the unprime.
Well, listen. Do you agree that the back end is going to be along this line, always.
Yeah.
At any point it will be along this line somewhere, so it will both be at some point on the x prime frame as it will be on the x frame, yes? It might be there on different moments in time, but it will be there at some point. Maybe what confuses people a little bit here is that they think maybe that world lines are fixed to some coordinate frame. But so, this world line is for this guy, and this world line is for this frame, and this world line is for that frame. But that is not true. A world line is just a world line. The only thing that differs from observer to observer, or if you will, from coordinate system to coordinate system, is not the line, it's the values that you measure along those lines. But the line is there regardless of. So maybe
the two line are basically kind of the word line of the plane itself, like the parallel lines.
Yes.
Yeah, it's just like if the plane was just a dot, it will be just like the.
There will be just one. But
yes. The value is just like okay.
Yes.
And the fact that it changes just means that okay, yeah.
Now, the fact that this one which is for funsies, right? I mean that it also has an interpretation, but not the one that we're looking for. They say the plane or the spaceship has a fixed length, so that means that its world line of the back end and the world line of the front end must have a fixed distance with respect to each other. And it does. Look, well, I didn't draw it very well, but this should be a fixed distance. Yes.
Going back to the gluing thing, so
but just to be sure, the gluing thing is just a funsies tangent, okay?
Sure.
All right.
But so with respect to the x prime,
yes,
the glued back end would move.
Yes,
Reference
of course,
frame, right?
yes.
Okay.
Because we'll move along with us.
Oh, yeah, I agreed.
For us, it's at rest.
Yeah, for us.
For the x prime, it's moving.
Exactly, and okay, I'm going to draw line anyway. But then I'm going to remove it for once and for all, okay? Because I'm going back to the actual exercise. So if the backhand will be glued, then it will move along this line. That will make it at rest in our frame. It will not be at rest in the primed frame.
Yeah.
How can you see that? Because in the primed frame,
it's not parallel to the.
It's not parallel to its CT primed axis.
Yeah.
Which makes sense, right? I mean, if it is moving, if it is fixed with respect to us, it will not be at the same location as by the other guy. Now I'm going to move this wherever. Okay.
No, but even if it was parallel to the CT prime, it would be moving, right? It has to be
according to them, if it's parallel to the CT prime, it's not moving.
Right now, it's not moving.
Is it?
This one, not the glued one. This one is not moving with respect to the prime frame, because it is always parallel to the CT frame.
But the x prime value is changing over time.
No, it isn't.
No.
Isn't?
It's constant.
Because it's going like that. Oh, wait.
Yes.
Yeah. Okay. Yeah.
But the grid of the x prime frame has all its lines like this.
Yeah.
It is the same line.
It's within. Yeah.
So it's at the same location. So you can ask me at some point, oh, but what is the distance between here, the front and the back end? Well, it's still 1,000 meters.
Okay.
Anyway, now let's move on. It says, blah, blah, blah. At this time, and they mean now, I find sometimes it's a little bit sloppy in their phrasing of the exercise, but the way that they say this is as follows. Just as the nose reaches us, here, both the clock and ship clock node read T0, okay, there's that. But when they are going to see where the back end is, they're not looking at this point, they're looking at this point. Why? Because they're measuring front and the back end at the same time. So we're now going to look at this point from now on, not this point anymore. Now, they're not extremely clear in how they phrase this, but they say, at this time, that point, what does the clock in the tails ship read? Now, if we were talking about this point here, I would ask what time is it at this point? We would say 0. Why? Because this point and that point are along the same timeline in the prime frame. So yeah, this point and this point in the ship, the nose clock and the tail clock read the same time. But they very subtly switch events. We're now looking at the moment in the ship when the unprimed people look where its back end is. That's not this point, that's that point. And now you see all of a sudden, wait a minute, now the nose clock and the tail clock will not read the same time anymore. And the question is, what is that value? What is that value that is now read at the moment that the at home people check where the back of the ship is, this point, what time is it in the back of the ship.
So we take the parallel to the x prime frame.
Yes.
And we see where it intersects the
Exactly.
CT.
And this you know, yes? If you want to know for any event along any point in the space-time, you want to know when it happened in some person's frame, take the other axis, draw a line parallel, and my arm is not as straight as a ruler, but it should be something like this. Okay? And where it crosses here, and this is the timeline of the nose of the ship, this tells you what time it is in the nose of the ship.
Why is it so tilted?
Yeah.
Sorry, what is that?
Why is it so tilted?
It's not parallel.
Oh, is it?
That's parallel.
It's like.
Should it be here?
Yeah.
Yeah. Yeah, I was.
Trust
yeah.
me, get up close to the board and try this yourself, okay? It's extremely difficult.
Once again, why is it when it intersects the CT prime and not when it intersects the CT?
No, but because we wanna know what their clock reads.
Yeah, so you need to take the line of simultaneity in the prime frame, right?
Yes.
I get why we get the parallel one, because we want like...
Still very crappy, by the way. It should be lower still, I think. But
But we will measure at CT. We only will see the...
we have to be very clear what things mean, yes? This is where, if we would measure where the back of our ship is, we, I'm sorry, we was going to be the people who are not going to know. Okay, if the ship people are going to measure where the back of the ship is, this is what they will see. Now, if we, the non-ship people, are going to check where the back of the ship is, and we make sure that we do it at the same time as we check where the front of the ship is, we were going to see this.
Yeah. And if we need the time, then we just draw the line, but it's on our CT that we are looking, no? Like, it will be on our axis.
Well, what is the question? No, what is the question? Is the question, what does the ship clock read at the moment that we have checked where its back end is, or is it what do they
what do we?
Yeah, but who is we? Who is we? Are we the people on the ship or not on the ship?
So what people not on the ship will see when they measured the. Not when they measured, but when the tail reached 0.
Yes, but
yeah, but where? Measure where? On their clock or on the clock on the ship?
So on our clock.
Yeah, but that is 0 because.
Yeah.
No, but when it when B reached 0,
yes.
We reach X 0. What will be our reading on
X0
our
is
clock?
No, X0 is there. You're talking about something else again.
No, but sorry.
Yes. Okay.
So there is the nose and the tail.
Yes. Nose, tail.
Okay.
Yes.
Is the question what we will read when the tail of the plane? What we will read when the tail of the plane reaches 0.
No.
Oh, okay.
That is not the question.
Also, because we already know that it's 0.
But no.
When we read our clock, what time is it?
When the tail.
He was introducing a different event now. What he was talking about, and I think the question we'll ask it at some point later, is okay. At some point, the tail of the clock will, the tail of the ship will pass us. Yes.
Yeah, that's
okay.
Okay.
Now that will happen. Here.
Yeah.
Okay. Because this is where we are, and we ourselves are always on the axis 0 line. This is where the tail of the ship goes, and where they cross. This is the event of the tail crossing us.
Yeah.
But that's not the exercise that we're doing now.
Oh,
the exercise that we do is if if we check not when the back of the ship is passing us. No, we stand here. The back of the ship is over there. We check where the back of the ship is.
Okay.
That is that event.
Yeah. Okay.
So the ship passing us, we wait until the ship has passed us. That's this event. I just realized this is on YouTube, including my writing on the wall. Anyway.
See that happened before.
Yeah. Oh my God. Yes, you're right.
Okay. So we know where is the tail that I get.
Yes.
But for us, the time where for us it's 0, where like. So at that position. The second point on the x-axis, at that position we know that it's at 0.
No, we know that we checked where the back of the ship is at time 0.
Yeah.
Okay. But that's not the question. The question is, at the moment that we do the checking of the back of the ship,
Okay, yeah.
what time is it on board of the ship?
Okay,
So
okay. It's for them. Okay, that's makes sense.
Yeah.
Okay, I thought it
Okay,
was
so-
in our frame.
No,
that
but
we-
listen, the question is
Okay.
the way that the question is phrased is extremely brief, because it says at this time, and then you have to figure out what they mean.
Yeah.
Now, what they mean is, I think it's a little bit too brief. I tried on the exam to be more elaborate on what I mean, so there's no ambiguity. So again, the question is, we measure where the back of the ship is.
Mhm.
We find that it is here.
Yeah.
Okay, and then we ask at the moment that we do the measurement of the back of the ship, what time is it on board
okay.
of the ship?
Okay.
Now, this event, our measuring of the back of the ship, you find out what time it is on board the ship by doing this.
Yeah. And this is why it intersects the T prime thing. Because I
Yes.
thought it was in our frame.
No.
It would be, and then I was
No,
like,
no,
there is no point.
No,
Yeah.
there's no point. I mean, I
Yeah.
know exactly when this happened
Yeah.
in our frame at T0. We made it that
Yeah,
point.
that's-
Anyway, so if you would do the actual drawing and you do it on scale, you would find this number. Now I know what the original numbers was when the exercise was still about 3/5 of C, then this was 600. Now I don't know what is 1/1/5 because the gamma is now a completely different number, so you'd have to do the measurements for yourself, but fine. Okay, so that solves that exercise. But you see how careful you have to understand what event you're talking about. And sometimes I just find that the book is a little bit ambiguous in what it is that mean. All the questions that that you could read in there are valid. It's just sometimes you don't know which of the two questions that is in the same phrasing is meant. No, this is what they meant. We move on. How long does it take the tail of the ship to reach us? Now, it
That
just so
was,
happened that we already,
yeah.
we just did that, right? So this is where the tail of the ship moves.
Mhm.
If you want to know where things meet, well, you take where your line is, how you move, you take where the other thing is moving and where they meet. This is how we move. We stay at this position, but we do move in time. This is our world line. This is the tail end of the ship's world line. And this
Oh, okay.
is how much time we see the ship take for us to have its tail. Now, this is an extremely elaborate way of finding this number, yes?
Yeah.
Because there's a much quicker way, don't you agree?
Yeah.
I mean, how long is a ship, as seen by us, it is 1,000 meters. For them, how is a ship longer or shorter for us?
Shorter.
Yes, Lorentz contraction, yes. And again, I don't know the gamma for C, for V is 1/5, but some number comes out. So you know that the value that we are going to measure, no, I'm sorry, I'm doing a different exercise now, the length of the ship.
No, but it's correct. It
Oh
has
no,
to
yeah,
be-
yeah, no,
it has to-
yeah, everything clicks together. Thank you. Okay, so no, I was calculating the distance. I thought no, I was looking for the time. But yes, with that distance, I'm going to calculate the time.
Yeah.
Okay, so the length of the ship, as seen by us, is going to be whatever Lorentz contraction of 1,000. That corresponds to V is 1/5c.
Yeah.
And that gives us how wide the ship is. How long that takes for us to pass? Well, that's just your high school physics, right? Because it's that distance. Divided by how fast it goes, 1/5 over c. Some number comes out, that's the amount of time. I will promise you, if you do this on scale, it will be this amount of time. But I have to say that is an elaborate way of doing this exercise.
Mhm.
Okay? Guys, given the time, I would really like to spend some time on 611.
Okay.
Because there's a little extra in there that isn't in this one.
Yeah, with the speed of light thing.
Yes, it's in the line now.
With like, oh yeah, it's the middle line that we have to check.
Yeah.
Yeah.
You know, I feel like not erasing this because the biology group is coming in. Oh yes, to leave it up, okay?
It's not long enough to.
And everybody walks out having understood everything, okay? You're very happy because it's extremely clear.
Smiling.
Just to reach here again, right?
That was so obvious, you know.
But it's not long enough.
Or maybe like, oh, it's so hard, but you know, we're
It's
so
just-
smart.
It's never.
Yeah, it's a bit difficult, but you know.
But you know,
Two
once you get
rounds.
into it, can you
Really, like fake modesty, you know,
So
the
we
worst
can-
kind.
I think
By some
was
creative.
so difficult, but I get it.
I think
You
this
know.
has to go.
Okay, guys, 611
Let's do
is
some
one more
creative,
time. The book
That
talks
it
about
doesn't-
exploding suns. They just keep on putting this trick on us, okay? Now, again, I'm not going to draw things on scale, but it's mostly about pointing out where events are and how you will project, and then you can actually do the measurement yourself. Suspecting that the sun is about to blow up, scientists board a spaceship and proceed away from the sun at 4/5 of c. Okay, so we are going to
Yeah.
take as this point, this event.
Whoa.
The labeling.
So this is wrong, yes, thank you.
How much?
450.
I don't know, it's possible. Go on.
People, what we have here is this point here in the center is we're going to take that as the event of the ship's departure from the sun. So this location of the sun and its departure. By the way, that immediately tells us what the world line of the sun is. Right? If this is the sun frame, then this is going to be the world line of the sun. It's good to keep that in mind. This is going to be the world line of the ship.
Yeah.
Right? So it makes it easy to come up with conclusions in a moment. Now, what they say in the exercise is the sun does explode when we are en route, and at some point we get the gamma rays coming from the sun's explosion. Now, they're not extremely explicit in it, but when they say gamma ray, they mean a light flash, because gamma rays are just a form of electromagnetic radiation. And if there's one thing that you know from last Tuesday, is that light must go with C.
Yep.
All right? So, let's suppose that the arrival of the gamma radiation at our position, and you know our position is by definition on the CT prime frame, the arrival is going to be this. This event is arrival of gammas. Okay, now, we're going to ask a couple of questions on where and when did the sun explode and such, so it would be good if we draw the world line of that gamma ray that arrived at us. The light itself also has a world line. Yeah. Fortunately, light has a very easy world line. It's 45 degrees in everybody's frame. So again, my drawing is a little bit crappy, but suppose that this is, here's a world line of a gamma ray. By the way, this is also one. Which of the two should I take? I mean, both of them are okay. Both of them are light coming to you, yes? Moving forward in time, coming to you with the speed of C. Which one of the two should I take?
On the left, right?
Yeah.
This one?
The one on the left.
Not this one?
No.
Why this one?
Because the world line of the sun is on the right, on the left. Sorry. So the light will departure from the right. The left.
Yeah, but
right.
we need to. The lights need to be a certain position to reach us now.
Yeah. So
that
when the
works
sun
to
is
detect-
at the
Works, yes.
The light.
Well, one's moving forward. Oh no, never mind.
Well, both are
gonna
moving.
say-
Both are moving towards x. Yes, the light is
Yeah.
moving in direction of increasing x, and the ship is also moving in direction of increasing x. But isn't that what we want? Because the sun, we are already en route. The sun exploded somewhere in our back, and we expected the light to come towards us from the sun, right? I mean, it's in the same direction as we are moving. It might be faster, but it's the same direction. So if we are moving in positive x direction, then the light must have as well. To be sure, there is maybe a light ray coming from this one, but that might be somewhere over there exploding, somewhere in front of us instead of in our back.
Yeah.
So this is the light ray of the sun. Not the light ray, excuse me. Yeah, it's a world line of the light ray of the sun. Alright. Now, the first two exercises here are just draw a couple of pictures. That we're not expecting you to do this by Minkowski's. We are, so we're going to immediately skip to exercise C. In the traveler's frame, this way. How far are they from the sun? Here. At the moment that the sun explodes.
How far in whose frame?
In
In
their
our
frame.
frame.
Yeah. Okay.
So that is one of the questions. So the question is, at the moment that the sun explodes, how far are we from the sun? How far do we see that we are from the sun? Now you tell me, where's the sun's explosion in this?
In the intersection of the
CT and
The light beam.
like you see if we CT and the intersection with light, that's when the sun starts to burst.
Well, I mean, this line is where the sun is at any moment in time, yes? And it is somewhere along this line that the sun explodes. But we also know that it arrived here. So this is the only point along the sun's world line where its light could have reached us. Oh, by the way, there's one more point of information that we haven't put into the picture. The exercise tells you that this is 2 light years.
Yeah. But the question is like, how far are we from the sun? Oh yeah, because it's already like it's not the first question.
No, I skipped one.
Yeah, okay.
So here the question was,
Yeah, how far are we from the sun in the like prime frame?
Yes.
And then they ask for when did the sun
This
explode?
is sun.
Yeah, in depth
Oh,
frame.
no.
But they
this
first
should
ask
be
in
sun.
depth frame, not in the
You took this as the sun
to them
Why?
in the T prime frame. When did the sun explode?
because it's the light cone.
Yeah, what do
Because that what we see here is like they
It's not the sun, it's
what
the
they
light.
yeah, that was the question.
But I haven't done anything yet. The only thing I've done here is
Yeah.
I pinpointed
But this.
what point in this whole space-time diagram corresponds to the sun's explosion.
Mhm.
I haven't calculated yet where it was, when it was,
Okay.
seen by whoever, and just told you this is the point
When
where
the
it
sun
happened.
exploded.
Where's the explosion itself? Now,
It's not like it is going at the same
yeah, what time did the sun blow up in the traveling frame? So what time is it when this happens as seen by the people in the ship?
The sun is itself is not traveling.
So we have to do the parallel of the x prime, right?
So,
This is the
something like
sun.
this?
Yeah.
That's
Yeah.
the sun
Yeah.
itself.
Okay, do you agree with this?
Yeah.
everybody?
Yeah.
This is the thing that we want to know when it happens. So we have to take some parallel projection of this thing, and we're projecting it on the traveler's time axis, because the question is, when do the traveler people see it explode? So take this parallel one, again, like drawing is very crappy.
But not this.
So we get another event here. Sun's explosion.
Mhm.
When the light of the sun's explosion reaches us,
Mhm.
this is the moment in time that the sun explodes as seen by us.
Yeah.
And I shouldn't say seen, because seen is when the light
Yeah,
of the sun,
yeah.
but when it happens.
Yeah.
Yes? Okay. Now, and then you can just read off what this number is, and some number comes out. Does it make sense? Because this is when the sun, yeah, that makes sense.
Mhm.
Because the sun exploded here. I mean, it's supposed that this is 2 hours or so. I have no idea. I'm just making up numbers now. But this is 2 hours, and this is 2.5 hours. It means the sun exploded,
Years.
and then half an hour later we saw the light.
Mhm.
By the way, that gives us immediately that we know where the sun was when it exploded. There's at least two ways that we can find out in our frame where the sun was when it exploded. Yes.
Our frame is the
Oh
ship
yeah, I'm sorry, the
or-
ship's frame, the,
Okay.
the,
Oh,
the
yeah.
traveling frame. So here's when the sun exploded. How do we find where it happened?
So we take c and we multiply c by the time interval between the
Yes.
arrival of the light.
That is one way. So that's absolutely true, because the difference, the time difference between these 2 points is when the sun exploded, as in our frame. I shouldn't say as seen. In our frame, and this is when we see the sun explode, because this is when the light of the sun, of its explosion, arrives on us. So the time difference between the two is apparently how long light must have traveled between the explosion to reach us. Now that times how fast it has moved,
Yeah.
c, will give you the distance. So this time distance multiplied by c will tell you how far away the sun was when it exploded. So that's one way of finding it, but there's a second way of finding that number.
Using the graph.
Using the graph, yes, but how? So here's the sun's explosion, I want to know where it happened.
Integral, I think.
No, parallel.
Because
But you throw the parallel to T.
Oh, okay.
I'm doing my best here, but this is meant to be a straight line.
Wanna know
Okay,
where
so
it's parallel
Here's when the
to
sun exploded.
CD.
Yeah, and we want to know where in the primed frame it happened. Now, you know how to do this. You have to project this dot on the primed frame.
Mhm.
So you have to take it parallel to the CT primed frame. That will give you, again, as parallel as I can draw it, it will get you here. That's a negative number.
Mhm.
Does it make sense to you?
Yeah.
Yes.
I mean, your sun here is going to be the exploding sun, okay? The spaceship, you're not exploded yet. Okay, now you explode. Okay, that's, well, okay. He's right, I mean, there's no sound in space, so he's right, okay? Okay. Then, as seen from my frame, it happened in the back, right? At a negative amount of distance. That's this number. And I promise you, again, this is not on scale, but if you would draw the picture, this number, or this value, should be the exact distance as this. In values, there's a C in between, but that's exactly that C. So anyway, if you would put your ruler here and you put your ruler there, you will get the same distance along your ruler.
In the correction, I thought there was no negative number.
What do you mean?
I mean,
Maybe I didn't see
you
it.
take the distance, okay, you don't need to put a negative number, but it's negative, it's a physical meaning in the exercise.
Oh yeah, sure.
Okay, at what time do the stay-at-homes, assuming some survive, so the books gives us that at least, assuming some survive, at what time do they say that the disaster happened? So here's when the sun exploded. What time was it when that happened for the people at the sun itself? That's very easy.
City prime.
City.
That's it. Read up that number. That's clear enough.
Stay at homes.
By the way, this amount of time, so this one, up to this point, and that one, I think there's some time dilation in there. You should be able to do this just by time dilation, right? Because for the sun people, the explosion and the departure of the ship explosion happen at the same location.
It's the shorter one. It's only from the red to red, not the black to the thing, because otherwise we have the speed of traveling.
Give me a moment to write this down for a moment. We have two events: the departure of the ship and the explosion of the sun.
Yeah.
This amount of time is how long it takes is seen by the stay-at-homes. Some number comes out. I think that's in the time dilation there will be this number, yes?
Yeah.
Because it happens at the same location for those people, so they get the gamma. And this projected here is how much time it takes as seen by the nun, the traveling people. That will be this number. So that means that if you would measure this value and you would measure this value, that should give you gamma. If you take the ratio, that should be exactly that gamma. It's a fun exercise, so if you have nothing to do, right? Check whether that's true. How are we on time, by the way? I literally have no idea.
5 minutes over.
5 minutes over, okay. Then I think this is quite clear how to do these exercises, yes?
Yeah.
Now give me a couple of minutes to say something about the exam. The exam will consist of 4 exercises. One of them is an exercise, just like last time, on conceptual interpretation of things. As in, I'm going to ask you, here such and such, explain to me blah blah what that means or in this context. More I'm not going to give you. Second exercise is going to be an exercise where I'm going to ask you to solve an exercise along the lines of these. But I'm going to ask you first to do it by transforms, actual Lorentz transforms, algebraically, and then by Minkowski's. And then check whether it's correct. Then there's a third exercise. It's going to be a paradox again. I'm going to leave it up to you if you want to solve it by Minkowski's or by Lorentz transforms with formulas. And the final exercise is something where I'm going to let you calculate a Lagrangian thing.
Oh no.
I've got some people who were happy with that actually. They said, oh yes, finally something that I can just follow the math.
Yeah.
So this is what I will give you. Now,
well, when are we gonna do the?
Yeah, well, I actually, when I sent out the invitation, I got about 8 written responses of the 29 people. So it's hard to do statistics on that. So I haven't decided yet. So
I thought we.
So if everyone emailed, I thought maybe we will
discuss it now. So
no, because we're one group short here. So I would rather also if you don't have an opinion and both days are fine.
Can we just write? Can we just
on
write it down,
paper or
everyone,
something.
and then we have half of the
end.
opinions
But
already?
then I have half. But why do I get the other half?
By
Maybe
email,
she has both.
like suggested before.
Yeah.
And we don't have to email.
Oh, I agree.
Yeah.
Okay, so let's do it like this then. This is.
I can't do Monday already.
Monday.
No, I
Monday, pre-Monday.
I can't do Monday.
No. I'm going to ask you when you go out. Put the dot there and put only 1, yes? I can actually count. And I will
Can we make it like
Is this for when the you raise the other one?
Can it be like a live?
So on your way out, put the marker in one of the 2 boxes, and I will have at least half of your opinions. Secondly, is there something that I can provide you with aside from us meeting on Monday or Tuesday? Is there one particular thing that you would still like to see? Please don't let the answer be either give me the whole exam beforehand or give me every written solution of every exercise. But maybe there's something that we really feel, well, I could really use some of this and this, and I can try to provide you with that before the exam comes. Feel free to think about it. You can send me an email, but
Maybe
I would like to prevent having 29 emails with different.
Maybe run again a paradox like bit hard paradox like exercise. So they always take time, so maybe if we...
How about this? On this Monday, Tuesday thing, we are going to do a solve on paradox. One of the exercises was a paradox thing. Let me do it in full detail in both Lorentz transforms and with Minkowski diagrams. So you've seen it both. So that was a train and tunnel paradox, right? With the lasers and such. I'm going to do it in both ways.
Oh, and the rabbit and hair thing also.
If
you
you
can
want
do it.
we're going to meet each other for 2 hours, so I'm sure we can squeeze it in somewhere.
I had no clue where to start. I was just like, oh, where? So the rabbit, the hair.
Yeah, that was a difficult one. I agree.
Plus it was at the end.
Yeah, the thing is like it was at the end. You're already like...
Yeah, you're done. No, at the end you don't care anymore. I don't know why.
And
but at the end
for some
no one
reason,
cares.
and the time
Was
also.
it about the information class?
Feel that I had like...
Yeah, that's why at the end I was like, oh no, wait, and then wrote something new, and I was like, oh no, wait, and then kept on going.
That was right, like with my drawing for the whole page.
Now, people, again, I would like to provide you with whatever you need, as long as within reasonable bounds. So, if you do feel like, well, I really have to see the solution to this exercise, and there's really no other way than me for you to get the solution to this problem, feel free to do so. As a tip for all, the book, chapter 6, 7, 8, and a little bit 9, are filled with exercises that you can just basically choose if you want to do it by Minkowski diagrams or by Lorentz transforms. And as you know, the odd numbers one have the solutions in the back. Okay, so if I can give you a tip, make a selection of these, even if it's exercise we haven't done in class. Just make it either by Lorentz transforms or by Minkowski or by both, and check the answers at the end. And check your Minkowski and your Lorentz transform answers. Yes.
Okay.
Yeah. Okay. So I think you have ample stuff to work with.
6, 7, and 8.
6, 7, 8.
Yes, those are very good chapters. And go for the odd numbers one, so you can check with the back.
And maybe more exercise on the language because there is no in the book. No.
That's true.
Yeah.
So if you could just like
that is good advice. We'll do that. Yes. That's very good. No. We'll put on a lane.
Yeah, for the regression because we don't have anything else.
That's a good idea.
Yeah, because I mean, in the book we have something.
That's a good idea. That's exactly what I was looking for. I asked the question. This is something I can provide you with. Okay, guys, thank you. See you in a couple of days, I think. Yeah.